Hi everyone, in this week's Scholarship Chemistry session, I'm taking up question 3A from the 2018 exam. In this question, we're given a really interesting context where we're told that the soil in New Zealand is low in iodine, and hence the food grown in New Zealand will have low levels of iodine. So a diet deficient in iodine can lead to health issues, so to increase that in our diet, it can be added using potassium iodate. The Australia-New Zealand Food Standards Code requires iodized salt to contain between 25 milligrams per kilogram all the way up to a maximum of 65 milligrams per kilogram of iodine. So, what exactly is the question? It's to calculate the lower limit for the titer values, meaning the volume of titrant that we're using in a titration when we're trying to quantify how much iodine is in a sample of food. That minimum amount of iodine that needs to be present in food is, once again, 25 milligrams per kilogram. So, what's this question about? Really, it's asking us to, if we were to do a titration to quantify how much iodine is in food, we're trying to figure out how much volume of titrant, and that titrant is sodium thiosulfate, should we expect to use to titrate a food sample with exactly 25 milligrams per kilogram of iodine in it. So what's happening in this first step? The first step that's happening is preparing the actual food sample. So a 50-gram sample of iodized salt, so that's salt with some iodine mixed in the form of potassium iodate, a 50-gram sample of that is added to a 250 milliliter volumetric flask over here. And it's made up to the mark with distilled water. The mixture is shaken, okay, the salt's dissolved, all that sort of stuff's happening. Now, of that sample, 50 milliliters of the total 250 mils in the volumetric flask is taken out, transferred to a conical flask. It's mixed with some HCl and some potassium iodide just to prepare the sample for titration, because what we're actually going to titrate is I2, or iodine. And I2 is formed when the iodate reacts with the Ki and the HCl. So this is all just about preparation. The details aren't really important except for the stoichiometric ratios in this balanced equation you see down here. For every one iodate molecule there are 3 moles of iodine. So it's a 1-to-3 ratio between 1 mole of iodate and 3 moles of iodine. That will be important in the end. Okay, so all we've done really is dissolved our sample in a flask, taken a small volume of that sample, and prepared it. Remember, this question is all about quantifying the exact volume of titrant we're going to be using in our titration. That titrant, once again, is sodium thiosulfate. So we need to figure out, if we're going to calculate the volume, we need to figure out how many moles of sodium thiosulfate is needed to titrate the iodine. We also need to figure out the concentration of this sodium thiosulfate solution. Now, the first thing we're going to do is calculate the concentration of the sodium thiosulfate titrant, and then we'll figure out the moles of it, and we'll plug it into the equation, and we're done. So, let's calculate that concentration. We're told that the solution is prepared by placing a certain mass right here, 2.456 grams, of the sodium thiosulfate into a 100 milliliter volumetric flask and making it up to the mark. The solution is then diluted by taking 5 mils of that solution from the flask and diluting it to 250 mils in a volumetric flask. So we're doing a sequence of dilutions here to get it to the right concentration. So in the first time we make up the solution, we have a certain mass dissolved in a certain volume. So that's easy enough to figure out the concentration of, right? So if we're given a certain mass here, you see that to figure out the concentration in moles per liter, I've taken that mass, divided it by the molar mass of sodium thiosulfate, and divided it by the volume of that volumetric flask to get the concentration of the sodium thiosulfate in a 100 milliliter volumetric flask. Now, it's diluted once again. 5 milliliters of this solution is extracted and transferred to a 250 ml volumetric flask and filled to the mark once again. So we need to know how many moles is in 5 milliliters of this sample, and then divide that number of moles by 250 milliliters. So that you can see I've done that right here. I've plugged in the concentration of the sodium thiosulfate in the first flask, multiplied it by the volume, and we know concentration times volume, it gives us the number of moles in a sample. And then we've divided it by the total volume of the volumetric flask to get the true concentration of our titrant after it's been prepared. Cool. So this concentration is going to be really important. That's the concentration we're going to plug into this equation. Now we need to find the number of moles of sodium thiosulfate that need to react with iodine in this titration. So once again, we've just figured out the concentration of sodium thiosulfate. Now we're actually going to calculate the number of moles of iodate that there would be in a 50-gram food sample. We're going to do this because we can figure this out, and then using stoichiometric ratios, we can convert the number of moles of iodate into the number of moles of sodium thiosulfate, the thing we really want to find out in the end. So we know that there's apparently 25 milligrams per kilogram of iodine at the minimum in a food sample. So when there's that amount of iodine, we can convert that into a number of moles of iodine. You see I've divided it by the molar mass of iodine. And then because there is a 1-to-1 ratio between the moles of iodine and a mole of iodate, we get that the number of moles of iodate is 9.85 times 10 to the negative 6 moles. Okay, so we figured out the moles of iodate. The whole point of this, though, is to figure out how many moles of sodium thiosulfate there is. Before we do that, we have to remember that what we've just calculated is the total moles of iodate in the solution we made when we dissolved a 50-gram sample. When we dissolved 50 grams into a 250 milliliter volumetric flask, we actually took an aliquot, a small sample of the total volume in that flask, right? We're not titrating everything in this flask. We're taking a 50 ml sample out into the flask and preparing our sample, right? So there's actually a lot fewer moles of iodate in this flask than what there is here. When we took a 50 ml sample out of 250 mils, we've taken 20% of the volume out. So there will be 20% of the moles in here compared to what we had in here. So you can see right here, the true number of moles of iodate in our conical flask where our sample is going to be when we were titrating it is actually 20%. So 0.2 times the total number of moles of iodate in our flask. And we get that the actual amount of iodate is 20% of that value. It's 1.97 times 10 to the negative 6 moles. So that's the number of moles of iodate in our actual sample we're titrating. Now we're going to calculate the number of moles of sodium thiosulfate needed to neutralize that amount of moles of iodine. I shouldn't call it neutralization because it's not an acid-base reaction. We're talking about redox reactions. So let's figure this out. The first thing we need to keep in mind is that when we prepared the sample, there is a 1-to-3 ratio between the number of moles of iodate and iodine. And then in our actual titration equation, there is a 1-to-2 ratio between the moles of iodine and the moles of thiosulfate. We're going to take the number of moles of iodate we just calculated and convert it to iodine. So that's a 1-to-3 ratio right here. And then we'll take that number of moles of iodine and convert it to thiosulfate using that 1-to-2 ratio. So you see first I've calculated moles of iodine by applying that 1-to-3 ratio. And then I've calculated the moles of thiosulfate from those moles of iodine by applying the 1-to-2 ratio. And in the end, I've finally gotten the total moles of thiosulfate I need to react with the iodine present in this food sample. And I can plug it into our equation here. We know the moles now, we know the concentration. Let's plug it in, see what we get. Once again, just a summary of the two values we just figured out here. I just plugged them into that regular equation, and we get that 5.97 milliliters is the minimum amount of titrant we need to use to ensure a food sample meets the minimum requirements for iodine in it. So if a food sample really does contain 25 milligrams per kilogram, and we're using titrant of this concentration, we expect that the food sample should require exactly this much amount, or this much volume, of sodium thiosulfate titrant to prove that. I hope that makes sense. We'll see you next week for another problem solution. Thanks.